I'm at ETH Zurich, and today I will talk about the strong pinning theory. It's a framework of vortex spinning that students and professors in our group have been working on in the past few years. And in our recent paper, we extended this theory for the effects of finite temperature, and we addressed from the theoretical point of view the question of vortex creep. So in the beginning, let me flash this beautiful picture of another PhD student, Roland Villa, from our group, which describes vortices inside a superconductor. The vortices are interacting with the defects, and we know that defects are in fact essential to maintain superconductivity, because we want in the end to apply current to the superconductor. Current on this picture is represented by the yellow arrows, and by applying current, it produces Lorentz force on the vortices, and the Lorentz force would induce vortex motion, and at this moment the superconductor of course wouldn't be useful, because the vortex motion would result in energy dissipation and from experimental point of view in finite voltage, and we would then have finite resistivity. So this is when pinning comes to rescue us. If vortices are pinned to defect, they don't move provided the drive is sufficiently low. So for drive below the critical current, JC, we have no vortex motion, and then when the drive is sufficiently large, the vortices start moving. So the vortex, so it's like it's very important to understand the origin of this critical pinning force, the vortex spinning mechanism, and also the mechanism of depinning. And this is addressed usually within two frameworks called the weak pinning and strong pinning theory. The weak pinning is somewhat the traditional viewpoint on vortex spinning, developed mainly in 1970s by Larkin and Ovchinnikov. And here the idea is that the defects have to act collectively in order to pin vortices. So you can imagine that you partition your superconductor into some balls of a critical radius RC, and then you sum contributions from all the defects within this ball, and all those defects together are pinning the vortex lattice. But so then, like, the picture that we have about driving the vortex lattice and vortex depinning is that once we approach this critical drive JC, there is something very dramatic going on. There is some sort of avalanche-like motion when suddenly the vortex lattice depends from all those defects, and we very quickly approach this line that we would have without any defects. And this picture, it was shown in 2012 in this paper, is quite different for the strong pinning regime. So in the strong pinning regime, the idea is that we have a low density of defects. The defects are relatively far away from each other, so their action is not correlated. And then, because the action is not correlated, if you induce motion of the vortex lattice, at some point you depin from this defect here, for instance, but you still remain trapped to some other defect far away, because it doesn't know anything of what happened here. And as a result, there is still pinning force even if you are driving the vortex lattice. And so you can see that this current velocity characteristic, it remains shifted compared to the characteristic that we would have without any pinning. So in our project, we address the question of what happens with this picture when we turn on the temperature, because temperature enhances the vortex motion, it helps vortices to escape the defects. So before I talk about that, let me just say a couple of words about what we mean precisely by the strong pinning mechanism and how it works. So within strong pinning, we can think about vortex spinning as induced by individual defect. So imagine that we have a defect and we drag a vortex lattice in this direction across the defect. And so what happens on one side from the defect is that the vortex nearest to the defect is trapped. And then when we are dragging the vortex lattice further, it remains trapped for a much longer region. So you see that the pinning force exerted by the defect on the vortices on this side is larger than on the other side. So then on average you have a finite pinning force which is opposing the vortex motion. So then we can translate this into because this is just a picture for one defect, so in order to obtain the final pinning force, we multiply by the density of defects, and then this factor is some geometrical factor telling us if we have one defect, what's the probability that it pins the vortices. And once having this result, in like first approximation, it's velocity independent. So even if we are dragging the vortex lattice across the defect with a finite velocity, this force stays more or less the same. So we substitute to the dissipative velocity of motion, the viscosity times the vortex velocity is the driving force minus this critical force, and this gives us this excess current characteristic. So no vortex motion up to the drive JC, and then a linear characteristic for drives beyond the critical one. So now when we turn on the temperature helps vortex spinning, it enhances vortex spinning and vortex depinning. You can imagine that this process of pinning and depinning is always associated with some sort of barriers, and now with temperature we have means to overcome those barriers. So what happens is that we get trapped to the defect earlier than before, and we also deepen earlier than before. So let me compare it once again with the previous picture. So here we are trapped here and we detrapped here, and now, sorry. And now it changes. So you see that when you integrate this force, there will still be some finite force opposing the vortex motion, but it will be smaller in magnitude. So creep reduces the pinning force. So now in the simple picture we substitute back into the equation of motion. Now of course the process is more complicated, and there will be some weak dependence on velocity which will cause this curvature at this point, but when we go to high drives and high velocities, the pinning force is again approximately velocity independent, and as a result what happens mainly is that this critical current JC is shifted to some lower temperature normalized value JDP, and the whole current voltage characteristic is simply shifted. So let me illustrate it by some more precise calculations. So we came up with the formula. So now it's useful to rescale the axis such that the current is rescaled by the critical current, such that this transition is at point J equals 1. And then we rescale the vortex velocity such that we make this slope equal to unity. And then the vortex motion is described by this formula. So the blue part describes the blue straight line that you would have here. And this is basically saying that the vortex velocity is due to the drive minus the force. Everything here is rescaled by the critical force, so this is -1. And now when we turn on the temperature reduces the pinning force, so minus pinning force gives plus this term, and we can regard this term as like something extra that we have due to the temperature. So this is now plotted for different temperature compared to some characteristic size of the energy barriers that we have, this EP, and we see that it gives rise to 4 curves which are shifted relative to the t equals 0 case. So interesting point of view is that when we look at the differential resistivity, we see that at this deepening point, JDP, the resistivity increases fast from 0 resistivity. So this is where we have only something which is probably not even experimentally measurable to finite resistivity, and then it approaches the resistivity here that we would have without any pinning. So it's like and then like interesting feature is that so this deepening current JDP we define as an inflection point in this resistivity picture, and the resistivity exactly at this inflection point is 1/3 of the flux flow resistivity. So now like what is sort of characteristic for strong pinning is this long tail, that if you go beyond the critical current you don't have a collapse of the pinning force, but you have this long tail, and we are aware that they observed this long tail in some measurements from 2002, and so we try to fit our theory to the data. Before doing that, we have to be a bit careful, because here the critical temperature is 7.18 kelvins, and the measurements were done in a region which is sort of close to the critical temperature. And when we approach critical temperature, all the quantities characteristic for superconductivity, like critical current and this slope, they approach the normal metal regime, and therefore as we increase the temperature, the slope also changes here. So in order to apply our theory, we first have to rescale those curves. So we rescale them in a way that they all approach a single curve with the same slope, and then also and then in this critical region we see clearly the creep effects. So when you zoom in, now we see in this region this characteristic shift, that as we increase temperature, we simply shift the IV curves to the left. We can fit the parameters of our theory, and we get a fit for a reasonable set of parameters here. So now let me change a bit the viewpoint. So before, we are concerned mainly about this long tail, which is characteristic for strong pinning and persists beyond the critical drive. Now when we look at somewhat small drive, it's convenient to describe vortex spinning by a process that the vortex velocity is due to thermal activations above the barrier, and we express the barrier as a function of current. So now when we do the calculations, we get this vanishing, this nonlinear vanishing of the barrier close to the critical current, and now this exponent 3/2 is somewhat ubiquitous in physics, and I mean it's also present in this Josephson junction when we describe transport through Josephson junction as having this tilted cosine potential, and when we reach a critical tilt, the barrier vanishes with this exponent of 3/2. But for the case of strong pinning, the origin of the exponent is somewhat different. And so we can imagine that we can model the vortex lattice as having, so now when we concentrate on one vortex which is closest to the defect, we can imagine that we can represent it by some sort of spring, and then the tip of the spring is trapped in the pinning potential. It is this pinned state, and there is a free state when the spring is completely relaxed, when it is at the level of the vortex, and the free state has lower energy. So the vortex would like to be in the free state, but in order to reach the free state, it has to overcome this critical nucleus, and it has to overcome the barrier. And then, of course, like you apply here your driving force, and when this driving force is the critical force, the size of this barrier vanishes with this exponent. And why I'm talking about this picture is that I want to say that like one message of this creep and strong pinning is also that unlike what intuitive expectations would tell us, the barriers survive even beyond the critical drive. So now when we are in the driving phase, when we are up here, I say that we still have the barriers. You can imagine that now you have your vortex lattice which is moving. So this vortex here is moving with some finite velocity. And if we are at 0 temperature, it has no ability to overcome the barriers. So we simply deepin, there is no critical nucleus, and we deepin exactly at the moment when the barrier vanishes, and we just slide down into the valley, which characterizes the free vortex. But now when we switch on the temperature, even though we are in a sliding state with finite velocity, we have ability to overcome the barrier, and so the transition happens at this point where we are trapped we are trapped to the vortex here, and then we overcome the barrier and go to the free state. And so this is also another illustration why temperature reduces the pinning force, because here you can see that the spring is more extended than in the case of finite temperature, and therefore the pinning force here is higher than there. So this barrier description is particularly useful when we are when we study decay of persistent current. So having some superconducting slab and applying magnetic field, and then switching off the magnetic field, we quickly reach this critical state when there is critical current flowing around the sample, and like the force induced by this critical current exactly balances the pinning force that keeps the vortices inside the slab. And now when we turn on the temperature, there will be some leakage of the vortices due to the vortex creep. And this leakage of the vortices is described by this exponential activation of thermal activation above the barrier. And when we solve it, we get a slow logarithmic decay of current. And now this exponent that we have here is, of course, dependent on the exponent that we have in this expression for the barrier. And like this provides us some experimental way of measuring the vortex creep, because then experimentalists can measure this time dependence and take the derivative with respect to the logarithm of time to get the normalized creep rate. and the normalized creep rate is a function of temperature. And we show that in the case of strong pinning, having this nonlinear dependence of barrier on the current, we get a nonlinear onset of the creep rate as a function of temperature, and then later we approach the inflection point. And so like in some, like the conventional theories of vortex spinning, when the barrier is supposed to be linear in current, there is of course no nonlinear onset and no inflection point. And so we compare this with some experiments on iron-based superconductors, when we can see some signatures of such type of inflection point in a similar region here. So I think this brings us to the end. So once to summarize what we did, so we studied vortex creep from the quantitative point of view. We addressed this process of the thermally activated pinning and depinning, and we show that there is a current voltage characteristic which has this long linear tail. This is something characteristic for the strong pinning, and this long tail is conserved even if we switch on the temperature. We simply shift the current, the characteristic to the left. So I think that's I thank you for your attention, and if you have any questions.